Well, let's consider a reversible reaction from 1A to 1B, and the scenario is like this. If you have some A, then in that particular time interval, okay, 1 over 2 of it will convert it into B, and if there is some B, then a quarter of boy will be converted to A. And here is our initial amount of A and B respectively, and you have 40 A and with 0 B. So that for the setting of this reversible system, first of all for A, half of it will go to B. However, because in B there is nothing at the beginning, so that there is no transaction from B to A. However, there will be 20 A react to form B, and these two processes from A to B and from B to A, they happen simultaneously, but just this time because B do not have any particle at the beginning, so that we do not have the transaction from B to A, but you will see the concept later. Oh, after the first transaction is that half of A, it will become B. So here is the outcome after the first transaction. Is it okay with 20A and then 20B? Oh, and after this step, A again, it will give back half of its amount to become B. However, for boy, it will only convert a quarter of it to become A, so that originally it has 20 and then a quarter of it, 1 over 4 of it will be converted to A. So here are the two corresponding transactions. 5 of boy converted to A, and then 10 of A is converted to B. And here is the outcome after the second transaction. There will be 15A, and then there are 25 of B. And then you just continue the calculation, and in case that you got some fractional number after you divide by 2 or by 4, just use rounding off to do the problem. Say for example, in this case for A, it has 15 of it, and half of it should be 7.5, and then round it off. Then in the next transaction, X of it will turn to boy. Oh, and here is the amount of A to B in the third transaction, and then simultaneously for boy, a quarter of it will react. It means that 25 divided by 4 roughly equal to 6. So here is the amount from B to A, and here this 8 will be from A to B. Oh, and then after this stage, you can see that for A, there are totally 13 of it, and then for boy, wait a minute. There are 27 of it. Is it okay? Then you continue the process for A, that 13 divided by 2, it means that 7 of it will be involved in the next transaction. And then for boy, that is 27 divided by 4, it's just 6 point something, roughly equal to 7. So this amount of boy will be converted to A. And then you can see that during this transaction, the amount from A to B, that's the upper one, there are totally 7, will be converted to boy. However, at the same time, there will be 7 boy converted to the A. It means that there is no lag change for A and B. Can you see the idea? And we said that this system is in an equilibrium. It's because if you continue to process one or two more time, it will be still 7 of A converted to boy, and then 7 of boy is converted to A, so that there will be no change for A and B. And we said that at that particular moment, okay, the rate of A converted to B equals to the rate of boy becoming back A. And it said that it can be said that the equilibrium is established. So is it clear? Oh, and then at that particular time, you can calculate the ratio of boy to the A by number of boy divided by number of A, and the ratio is roughly equal to 2. And that is the first simulation. Oh, and then the second simulation is just similar. However, the initial points of A and B, they are different. Oh, in the second simulation, initially there are 40 of A, just the same. However, for boy this time we have 20 of it. And here is the initial point. Oh, and then we just follow the same ratio for them to react. Oh, half of A in the transaction will be converted to B, and this is the amount. And then for boy, a quarter of it will be converted to A, so that this 5 will go to A. And these two processes, they occur simultaneously. Oh, and then after this stage is the outcome after the first round of transaction. Oh, and then you continue the process. Okay, the half of A will be converted to boy. Should be this 13. Oh, and then for boy, a quarter of it will be converted, and now here are totally 3, 4, 5, 6, 7. There are 35 of it, so that 9 of it will be converted to A. Well, and then here is the situation after the second transaction. There are totally 21 of A, and then for boy there are 39 of it. Is it okay? Oh, and then for the final round of transaction, 21 divided by 2, it should be 10.5. That means the 11 will be transmitted. I mean, it will be converted to boy. Oh, and then for boy, 39 divided by 4 roughly equal to 10 of it. Oh, and here is the case after that transaction, and then you do the counting for A. Now it has 20 of it, and then for boy now it has 40 of it. So that in the next round of transaction you will see something. For A, half of it will be converted to boy, that means 10 of it, and then for boy a quarter of 40, that is also again 10 of it will go to A, and then A, 10 of it will go to B, and then this process just continue. For half of A will go to B, and then a quarter of B go to A. And then you can see that the transaction amount from B to A and A to B are just the same. We have 10 of the paper clip converted to another side. It means that in that system we again can say that okay, the rate of A to B equals to that from B to A, and we said that the equilibrium it has been established only. However, be reminded that during the process there is not a static equilibrium but a dynamic equilibrium instead, because at any time interval reaction is taking place. However, just the rate of the forward process equal to that of the backward process, so that you can see that overall the number of A and the number of B remains unchanged. However, things are happening. Both the process of the forward one and then the backward reaction, they are occurring at the same time. Can you see the idea? Oh, and then again, you can calculate the ratio of number of boy at this equilibrium divided by the number of A at this equilibrium, and the value is roughly equal to 2. Oh, and the idea to show you that is that okay, for the same process, if it is under the same temperature, then the ratio that converting from A to B and converting B to A, they remains unchanged. Then the ratio at equilibrium of B to A will be the same constant. Can you see the idea? Oh, show you one thing more is that is there only one way for the equilibrium to establish? You can see that in both of these simulation, one A is more than B initially. Then what if initially I just have boy? Can the equilibrium be established? Just have a look. Oh, and here is the first scenario. Initially we have 40 boy and then without any A. And again we obey the same ratio. Okay, a quarter of boy will be converted to A, and this is the situation after the first transaction. Oh, and then for the second transaction, half of A again, that is 5, will be converted to boy. And then for boy, 1, 2, 3, 4, 5, 6, 30 of it, and the half of it, it means that how many? 8 of it will be converted to A. So after the second round of transaction, here is the outcome. A, there are 13, and then for boy there are 27, and then you just continue. For A, half of it will go to boy, it means the 7 of it will be converted to boy. Oh, and then for boy now it has 27 and then divided by 4, it means that 7 of it will be converted to A. And now you can see that the equilibrium can still establish if we have B only but not A. And in chemical equilibrium is just look like the same. The equilibrium can be established from both sides of the reaction, can be starting from A or can be starting from B, or the situation you have some A and you have some B, the situation can still be done. Oh, and you again calculate the number of boy over number of A, then the ratio will be again just equals to 2. Can you see the idea again? For a certain reaction under the same temperature, it means that the 1/2 and a quarter ratio of the conversion from A to B and B to A respectively, they are the same. And then the final outcome, the amount of boy divided by the number of A will be just the same value. And in this case, it is equal to 2. Then it is applicable for all reversible reaction.